Welcome, ladies and gentlemen. Let's go ahead and take a look at your Bellwork today. And so we've got a problem situation where Sarah has been reading her book for the past week. After reading one night, she had 914 pages remaining. At the end of the week, she had only 512 pages remaining. Sarah thinks that she reads at roughly a constant rate. So those key words, roughly a constant rate, there's our cue that we might be using a linear model, right? A linear model for our interpretation. All right, let's determine the rate at which Sarah reads complete with units. And so the first thing we want to do is decide, just like in our creating and interpreting linear models activity packet, what x is going to represent and what y is going to represent. To do this, I always try to make a sentence in my head, right? Do the number of pages remaining depend on how many nights she's been reading, or do the number of nights she's been reading depend on the number of pages remaining? For this one, what makes sense to me is the number of pages remaining, right, depends on how many nights she's been reading. If she's read fewer nights, then she's going to have more pages remaining. If she's read more nights, then she's going to have fewer pages remaining. So I'm going to let x be the number of nights spent reading. The number of nights spent reading. I'm going to let that be my x quantity. I'm going to let y be the number of pages remaining. It's important that we're not talking about the number of pages in the book. We're talking about the number of pages remaining. Awesome. After I've designated my x and y variables, we can now get points. And so the given information is telling us 2 points that are on this linear relationship. Let's go ahead and get our first point. After reading for one night, she had 914 pages remaining. Go ahead and tell the class what point that represents in our linear model. All right, what point would that be? Caitlin? What point is represented by the first sentence? After reading for one night, she had 914 pages remaining. Awesome, thank you. What other point am I given based on the written information? Right, what's another point I'm given based on the written information? Anna? Awesome, thank you. Raise your hand if you have these 2 points. So these are the 2 points given in our linear relationship. Thank you. Let's go ahead and now determine the rate at which she reads. Remember, the rate of change in the number of pages remaining with respect to the number of nights spent reading, that's my slope calculation. So we'll go ahead and do our slope m is given by y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. And I'm getting 512 minus 914 all over 7 minus 1. And so when I do this, I got negative 67. Negative 67. Raise your hand if you have the numerical answer, negative 67. Keep your hand up if you know the units on this rate of change. What would the units on this rate of change be? Thank you, hands down. Caleb with the K?
Pages per night.
Pages per night. Nice job. Because my rate of change units in the y quantity with respect to x is always given by y units over x units. In this case, pages remaining over nights spent reading. So negative 67 pages per night. Nice job. All right. I'd love to do an interpretation of that. So let's go ahead and do a quick interpretation just because that's what you're going to have to do on the quiz. And so we can say the y quantity is increasing or decreasing, right, at a rate of my rate of change number and then y units per x units. So I'm going to go ahead and interpret this quickly because it'll be a good warm-up for our quiz. The number of pages remaining is decreasing. I know that the number of pages remaining is decreasing because my slope number was negative. So I know that the number of pages remaining is decreasing at a rate of 67 pages per night. That means after one night, right, of spent reading, I expect the number of pages remaining to go down by 67 pages. Awesome. What questions do you have about this first one? We've got our units. let's go ahead and write a linear model that gives the remaining pages p as a function of night n. So I'm not going to use, right, y and x. I'm going to use p and n. That's no problem. I've got my 2 points, and I've already got my slope. And so I'm just going to go ahead and use either one of those in point slope form, and then I'll change it to p as a function of n. So once again, I'll start out with like y minus y sub 1 is equal to m times quantity x minus x sub 1. Go ahead and tell the class which point you'd like to use for our model. Which point do you want to use? Read.
Let's go 7, 5, 12.
7, 5, 12. And so I'm going to use the x coordinate 7 and the y coordinate 5, 12 to generate my model from point slope form. So let's go ahead and do x minus 7 and y minus 5, 12. What are we going to use for our slope number? Right? What are we going to use for our slope number right there? Logan? Cool, thank you. I'm going to use the negative 67. So here's my point slope form. That's my go-to tool when I'm going to write the equation line on my own. I'm going to solve this for y and then call it p because the direction specified, I write the pages p remaining as a function of the night n spent reading. So let's go ahead and solve this bad boy for y. So I'm going to leave my 512 alone. I'll distribute through the parentheses. Negative times a negative is a positive. And 67 times 7, that looks like 420 plus 49. Is that 469? 469? Great. And then we'll go ahead and add over 512 last. 469 plus 12 is 900, 979, 981. Is that what you guys are getting? 981. And lastly, we'll go ahead and write this now as the number of pages p remaining as a function of nights spent reading n. So I'll go ahead and call this, bless you, p equals negative 67n plus 981. Raise your hand if you generated this equation, either in green or in black. Did you generate that equation? Hey, great work, you guys. That's awesome. Okay. So now what can we do with this? Well, let's interpret the y-intercept in the context of your model. So everybody identify the y-intercept. I want you to state the value, right? And then tell what it represents in the context of the problem. What does that y-intercept represent? So what's the value of our y-intercept and what does it mean in the problem? Jason?
The value is 981 and it is the number of pages Sarah started with after reading 0 nights.
Wonderful. Thank you for your interpretation. That's perfect. And so, the value is 981. And what does that mean? It means that after 0 nights spent reading, Sarah has 981 pages remaining. Right? That could likely be the number of pages in the whole book, right? It should be, when she starts, there's 981 pages remaining, right? And since she's reading Twilight for the 7th time, good for her. Well, good stuff. All right, let's go ahead and finish it out then. When does your model predict that Sarah will finish her book? What? When does our model predict that she'll finish her book? Well, what would be true about our model, P or N, when she's finished her book? Right? What would be true about our model, P or N, when she's finished the book? Jacob?
P equals 0.
P would equal 0. There'd be no pages remaining when she finished her book. So I'm going to import my model, P equals negative 67n plus 981. We'll purposefully set the pages remaining equal to 0 and solve for n the number of nights it'll take to have 0 pages remaining. So I'll go ahead and subtract over the 981. I'll divide by negative 67. And if you kindly do that with your calculator now while I'm writing, then I'll call and make sure with the class, and you can give me the decimal. So negative 981 divided by negative 67, what does that give me about?
14.64.
14.64. All right. So 14.64 is standing for n, right? It's standing for n. So this 14.64 has what label, has what units here, right? Kayla? Nights. And so it looks like it's going to take her 14.64 nights, right? And so in terms of the number of nights spent reading, how many would she have to read? Well, she'd really have to go into the 15th night. You see what I'm saying? She'd have to, after 14 nights, there'd still be pages left. So she'd have to read 15 nights. And so in the context of the situation, it looks like she'd have to read for 15 nights in order to finish. And at this time, I'd ask that you raise your hand if you already had that. So everybody get all the way to 15 nights. You guys are awesome. You're going to do great. Wonderful. All right, we're going to go ahead and check our answers, and we did this first one together, so I'm going to pause the recording while we take care of our homework check, and then I'll resume it for our discussion. Thank you, ladies and gentlemen. Let's go ahead and take a look at our goals for today. We're going to interpret sequences and find explicit formulas for sequences, really more as an introduction today, and we're going to do it more next class period. We're also going to graph and interpret graphs of sequences, and so that's where we're headed. A sequence is simply an ordered list of numbers or objects. Okay, and so this is a sequence. 3, 6, 9, 12. Our sequence here is simply a list of numbers or objects. And oftentimes there's a pattern that connects those objects in the list. Consider the sequence of numbers C. Describe how each term after the first is related to the term before it. So consider 3, 6, 9, 12, bless you. What's the relationship between each term and the one before it? Kenzie?
It's going up by 3.
It's going up by 3 each time, right? If I looked at the third term, because a specific item in the list is called a term, if I looked at the third term, 9, that's 3 more than the one before it. But if I looked at the fourth term, 12, that's 3 more than the one before it. And so we could say that each term is the previous term's value plus 3. Or each term is increasing in value. By 3. Let's go ahead and give an explicit formula for C sub n. An explicit formula, right, is a fancy name for a rule that gives us the value of the nth term. In other words, if I wanted to know the value of my third term, when n equals 3, and I plug it into my explicit formula, it should spit out 9. If I wanted to know my value of the fourth term, that is when n equals 4, when I put in 4 for n in my formula, it should spit out 12. Can we come up with a formula that gives us the value of the nth term? Well, I think so. I'm going to have n's in my formula, and when I'm plugging n for the term number, it should spit out the term value. When n is 4, C of n is 12. When n is 3, C of n is 9. When n is 2, C of n is 6. Anybody have a potential formula they'd be willing to share with the class? What formula does it look like? Max?
3n.
3n? 3n, let's go ahead and check. When I plug in 3 for n, my term number, it should spit out 9. Does it? Oh yeah, 3 times 3 is 9. When I plug in 4 for term 4, it spits out 3 times 4 is 12. Hey, this works. Good job. Thank you, Max. Let's go ahead and use a new explicit formula. Call it A sub n, which gives the terms in a sequence. When the term numbers are 1, 2 for the second term, 3, 4, and 5, I can calculate the term values in my sequence simply by evaluating my explicit formula. So an explicit formula is just a fancy name for a rule that gives me the term in the sequence based on the term number. First term, I can evaluate by plugging in 1 for n and working it out. Looks like 1 minus 2 times 1 is 1 minus 2, and that is -1. When n equals 2, 2 times 2 is 4, and 1 minus 4 is -3. When n is 3, 2 times 3 is 6, 1 minus 6 is -5. as you continue evaluating my explicit formula and generating terms, you can begin to see the pattern as well. So -1, -3, -5. Without evaluating, can you guess the fourth term value? Well, what's the fourth term? Abby? -7. Nice. -9, and so on. In fact, we could write these as ordered pairs, right? A sequence is a function. Every time I put in 3 for the third term, it's going to spit out -5. So each input is paired with exactly one output, which is the definition of being a function. And so all sequences, right? All sequences are functions. So let's write these as ordered pairs to drive home the fact that these are 1, -1, 2, -3. So we see that a sequence is a pairing, right? It is a relation. It pairs inputs that are the term numbers with outputs that are the terms in my sequence. Consider the sequence shown in this table. This sequence is called the triangular numbers. It's so called the triangular numbers because it starts, right, with an array of dots in the first row. There's 1 dot. In the second row, another 2 dots are added for a total of 3. After 3 rows in this array, there's a grand total of 1, 2, 3, 4, 5, 6 dots. After 4 rows in this array, there's a total of, that looks like bowling, 10, and so on and so forth. And so you see the pattern here? That's why it's called the triangular numbers. And you don't have to have that picture, but that's kind of fun. Let's take the domain of the sequence. Well, the domain, if I'm given a table, is simply the list of input values, right? X values. In a table, that would be oftentimes the first column or the top row. And so in a table, the domain would be 1, 2, 3, 4, 5 if I'm given a table. However, we're going to assume that this sequence goes on forever and ever, starting at term number 1 and going towards an infinite number of terms, as far as I want to go. So we'll say that this table is only showing us a snapshot. Therefore, the domain is all the counting numbers. That is, starting at n equals 1, 2, 3, 4, and forever after. In fact, the domain of all sequences will assume to be the counting numbers or the natural numbers. So let's go ahead and call those the counting numbers or the natural numbers. And we'll see that again. So the counting numbers start with 1 and increase 2, 3, 4, those numbers that we could count on our fingers and toes forever and ever. If we called the function t, then t of 1 would be the value, right? The value of my term when I'm looking at the first term, so that would be what? 1. T sub 2 would be 3. Go ahead and tell the class what T sub 5 would be based on my given information. So what would T sub 5 be? Jake? 15, thank you. That function notation, that Euler notation, right, is typically reserved for continuous functions, but not always. Sequences oftentimes have their own notation, which means the same thing. We just use subscripts. Instead of the parentheses in that function notation, that Euler notation we talked about last unit, oftentimes sequences use subscripts for their notation. So instead of using T of n, a common notation to use is a subscript for the input. The subscript is simply a label that's set lower and smaller than the regular text that tells us, that indicates, right, what term we're talking about. So it's called an index oftentimes because it indicates which term we're talking about. T sub 3 is 6. The third term is 6. That's all it means. So a subscript is telling you which term you're talking about. Sequences are discrete. That is, when graphed, they'd be disconnected points on the xy coordinate plane. So they're disconnected, they're discrete. as opposed to continuous graphs, which we're used to making, like the lines that you're going to draw in your quiz second half. Those are continuous graphs because they're connected points. Discrete graphs are disconnected points. And so I remember discrete functions have graphs that are disconnected points. Sequences are examples of discrete functions. That is, they're formed from isolated, non-connected points rather than continuous curves. But not all discrete functions are sequences. This particular function may or may not be a sequence. I just wanted to use the graph to show disconnected points. We're going to go ahead and make the graph of a sequence. It's easy to do so because each sequence, right, each value in the sequence is really an ordered pair. It's term number, comma, term value. So we can go ahead and plot those points just like we would plot points in the x, y coordinate plane when making other graphs. Let's go ahead and do some together. Let's use the explicit formula L sub n for a sequence equals 9 minus 0.5n. What we're going to do is graph the first 6 terms of L sub n. So what I'm going to do, just like we had n and t sub n in a table, I'm going to do the same thing, but I'm going to do it for n and L sub n. So I'll go ahead and do n is my term number, and I'm going to pair that with my term value, L sub n. Recall that the normal domain of a sequence starts with 1, those numbers that I can count, right? The counting numbers. And so I'm going to go ahead and choose 1 as my first term value and evaluate L sub n to get the value of my term. L sub 1 then would be 9 minus 0.5 times 1 is 9 minus a half is 8.5. When n equals 2, my second term is given by 9 minus 0.5 times 2 is 9 minus 1, and that's 8. When n equals 3, then I go down another half, I'd be at 7.5. N equals 4, 5, and 6 would pair out, I would round out my last 3 terms that I'm going to plot for the first 6 terms. So we go 4 would be what, 7, 6.5, and 6. Everybody good? Let's graph our sequence. Our sequence is easy to graph. We'll simply make points in the xy coordinate plane. So here we go. 1 comma 8.5 would be 1 comma 8.5. 2 comma 8, everybody plot it. 3 comma 7.5. Oops. 4 comma 7. 5 comma 6.5. And 6 comma 6. Looks like we got it. Notice how the graph of a sequence is discrete. It's disconnected points. Let's now contrast that with L of n. That is the continuous function using the domain of all reals, and we'll do it on the same axis. In the continuous function L of n, I can use the y-intercept as the first point, 0, 9, and plot that. I'll now use my slope, negative 0.5, right, to count out my rise over run and get additional points on the relationship. It looks like I go down a half unit for every one that I go over, and by golly, that's going to fall right on top of my sequence value. However, it's not discrete points the way a sequence is. It's connected like you're going to do on your quiz when you draw the line and do the arrows. So I'm going to do the same thing. I'm going to grab my line tool, and I'm going to go ahead and connect all those green points forever and ever in both directions. That's the difference between the graph of a sequence, L sub n, versus the graph of my continuous function, L of n. Everybody see it? Bless you. What do these graphs have in common, and how are they different? So what's something that these graphs have in common? Kenzie?
Both
They're both linear, right? This was a linear sequence, absolutely. So in common, they're both linear. This particular sequence was linear, and the continuous function was also linear. Good. Anything else they have in common? Libby? Yeah, they share, right? They share the same points. In fact, every time my input value for my continuous line is an integer that's positive, that is a counting number, then it's going to share a point. All the other ones it's not going to share, right? If there's non-integer inputs, then that's not going to be a member of the sequence. Good, so they share all those points that are blue. How are they different? Right? How are their graphs different? So what's one way they're different? Caleb, let's see. What's different about the blue plotted points versus the green plotted points? Are my blue points connected? Did I connect them with the blue line tool? No. Are the green points connected? Yes. My sequence is discrete for disconnected points, right? My linear function here, my L of n, is continuous connected points, and that's how I keep it straight. Awesome. Thank you. Questions about the graph? Yes, Abby.
You said the green points were connected, but there's only one green.
I overwrote these when I continued counting down and over, down and over, down and over, down and over, and then all of them would be the green line here.
Okay.
But yes, I can even make it like. Oh yeah, totally connected. David.
So for sequence, we're not like taking negative numbers.
Correct. The input values start at 1 and then go on counting 2, 3, 4. Correct. So we don't have negative inputs when we're dealing with a sequence, and that's another contrast. Good. Any other comparisons or contrasts you want to add? All right, let's go ahead and close it up then, and then we'll get to our quiz. So I want you to go ahead and think, don't call out. A sequence is a function. That's a true or false question. Don't call out, just think. Write it down on your paper, and then unless otherwise specify what is the domain for all sequences, be ready to share because I'm going to call on you. Okay, true or false? A sequence is a function. Raise your hand if you're willing to share. So a sequence is a function. Is that true or false? Naya? True. A sequence is a function. And so every time I put in the term value 3, it's going to pair it with 7.5 in the L sub n scenario. Every time I put in a 4, it will pair it with 7. And so a sequence is a function. So that's true. Helpful if I wrote that in the same color though, wouldn't it? Totally worth it. And lastly, unless otherwise specified, what's the domain for all sequences, right? What's the domain for all sequences? David? Yes, the counting numbers, starting with 1. So the counting numbers, or the natural numbers if you prefer. So we start with, we'll go gadget arm, 1, 2, 3, 4, dot, 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 forever. That's the domain of all sequences. Nice job, you guys. What questions do you guys have about our discussion today? I'm going to go ahead and stop the recording and save it and upload it to our Moodle.